Today's lecture is going to focus on engineering requirements and how to combine engineering requirements and customer needs to evaluate product concepts with house of quality. These slides are taken from Dr. Ertos and modified from his Transdisciplinary Senior Design course, but these methods are also something you'll find in a lot of other textbooks in the Dieter and Schmidt book as well. So a requirement is a documented physical or functional need that a design, product, or process must be able to perform. And what's important here is a requirement tells what the design needs to do, not how it does it. So later in the design process, after the requirements are figured out, that's where you come in and conceptualizing your designs to accomplish the task. And so requirement management requires speaking with the customers, identifying capabilities and conditions and attributes, and also it's not an easy task. It's more an art than a science often, although there are methodological steps that we're going to cover in class that help make sure that you consider all the requirements and write them in a way that's useful for an engineer. So ideally, you're going to go from customer needs to design requirements to specifications of exactly how the design is going to work based on components in the design. So the requirements are used throughout system development and lifetime of the design. You want them to capture the essence of your concept. They're going to drive your design, and you're always going to be looking at, are your decisions meeting your requirements or not? And they also need to be verifiable. So after you come up with a requirement, is there a way to test it? Is there a way to make sure your design is meeting that requirement or not? We're going to focus mostly on physical constraints in this class and as mechanical engineers, where physical constraints of the design might be what materials it needs, what weight and volume limitations, and by materials that would be like the material properties, not saying it must be made of steel, but saying it must have a certain stiffness or elastic modulus. Transportation and size requirements are often physical constraints. Other places you might be getting constraints from are social, so legal, ethical, aesthetic, health, safety, environmental regulations, and that comes a lot from the beginning to the end of the design. So how are you going to dispose it? And then economical comes into user needs as well. So an example of a physical performance or functional constraint, it would determine the performance limits of your system, such as the valid range of frequency it operates, the temperature range, the operation range, what's expected for the product. So you could say for one product a customer need is you want to control a system with operating pressure between 400 to 600 psi and a pressure vessel of 10 cubic feet volume. So then the functional constraint is the control system operation pressure, and the physical constraint is the 10 cubic feet. A good requirement needs to be as clear as possible. You don't want any uncertainty or confusion, especially since you're going to be communicating this with teammates and possibly your customers or people outside your team in the future. You want to define one requirement in a written statement at a time. So that means as you're writing your requirements, you want to avoid conjunctions like and or also and with. So saying something like the temperature has to be at least 200 degrees and the size has to be less than 100 cubic feet. That's two different requirements and you should write them one line after another. If extensive conjunctions are necessary for clarity, the sentence should be decomposed into shorter sentences, and each requirement should have a complete sentence with no buzzwords or acronyms. So try to keep things understandable to an engineer at your level, regardless of if they're in your project or not, rather than using jargon or buzzwords that might be unclear to certain people. So buzzwords also fall into the category of being vague and unverifiable terms. So examples are user-friendly Versatile, robust, approximately, minimal impact, easy. Those are all ambiguous words that mean different things to different people. So, for instance, the user must be able to set up the system quickly versus the user must be able to set up the system in under 10 seconds are two very different requirements. The second one gives you a quantitative measurement so that what's quick to somebody might be 2 seconds and what's quick to another person could be a minute. And each statement that defines a requirement needs to have the word shall in it, shall or must. And will should only be used for statements that provide information, the same as should. So the system must/shall be set up in less than 10 seconds versus the system will be set up in less than 10 seconds. The second one's improper because it doesn't have the same definition and clarity and assertiveness as the first. So these are examples of good requirements. The engine shall operate at a power level of 425 horsepower. An incorrect way of saying this might be the engine shall not operate less than a power level of 425. And the reason the second one is not a good way to write it is you're writing it in a negative form that makes the reader need to make like a logical turn as to what you're meaning. And it's also, more wordy that way when you write it in the negative. The tower shall withstand wind loads of 100 miles per hour versus the tower will withstand wind loads of 100 miles per hour. So will is not as constant as shall. So will means, in this sentence, it will withstand 100 miles per hour, but not necessarily always withstand that. So that's why shall is the more clear term. The cruise ship shall travel at the speed of 22 knots versus the cruise ship should travel at the speed of 22 knots. By using should, you're making it in a case that it's ambiguous as to what you actually want to accomplish, because if you don't hit 22 knots, if you only hit 20 knots, is that design okay or not? Or maybe you can only do 2 knots, and so that's way off from the 22 knots. But if 22 knots is the minimum, because let's say it needs to travel from one port to another port in a specified amount of time, then the 22 by saying shall specifies that it needs to do that, and any less isn't going to work for the design. So the requirements need to be realistic in what you can build. They need to say what the design needs to do, not how to provide it, because there's many ways to make a ship go 22 knots. You could reduce the drag, you could increase the power, you could be traveling on different days in different conditions. And then for the requirements, they need to be quantifiable, testable, and verifiable. So the 22 knots is something that you could easily measure the speed of the boat. You can test it, you can start and end it one day and see how fast it traveled, and then you verify that you met the requirement. If you're unable to determine, for instance, how fast a boat needs to go for a specific requirement, or in another case, you should use your current best estimate rather than keeping it ambiguous. So a good example is the boat should go 22 knots plus or minus 2 knots, because maybe 20 is okay, but 19 is definitely not okay. So the plus or minus 2 accounts for that spread. Another thing could be the 3 sigma accounts for maybe variability in conditions in manufacturing. But it's better to get a ballpark number there than to say something like the boat needs to go fast, because that's ambiguous and subject to interpretation. So one of your assignments, homework 4, is going to be turning in requirements, and I am going to look them over, and you should look them over as well to see if they meet the criteria we've talked about. And some of the checklists you might want to go over is each requirement correct and as clear as possible? Are the requirements technically feasible and realistic? Can you measure, test, and verify them? And are they specified in terms of units and values that are achievable? And by reliability, that could be something like, are you going to use the product one time, or are you going to use it 10 times? How many times should it work, or how many times should it cycle before it's expected to need maintenance or replacement? And one of the reasons you need to do requirements early is the cost of changing a design gets more expensive the further and closer into production you get. So if the design needs to go a certain speed, you need to know that upfront in the design process, rather than designing a boat that goes 15 knots, testing it, putting it out for evaluation by potential users, and then seeing it's not fast enough. You've already spent the time designing, building, and testing the wrong boat. And so you have to go back, and let's say you have to resize the engine. That likely means you're going to need to resize a lot of other aspects of the boat as well. So it's not just one simple change to fix the system. So for instance, by resizing the engine, you could come into problems, geometry of the boat itself. You could have weight problems. You could have cost problems come into play. You could have different fuel efficiencies that cause an issue. So a lot of aspects of the design depend on other aspects of a system. And that's why you need to really think about all your requirements beforehand, so that as you're picking components, you can pick them so you fit all the requirements the first time through the design. And then if things need to be changed slightly, it's not going to have as big of an effect on the rest of the system. So the requirements eventually turn into product design specifications. But another step in that process is using the requirements to see how they interrelate with each other, so that when you do something like change the engine power on a boat, you can see how it's affecting other aspects of the system. And we do this with a tool called House of Quality. And so I'm going to introduce the tool in this 2 weeks module of the class, but then we're going to have homework over it and do it with teams in the next product selection or concept evaluation aspect of the course. But we're at least going to start it here in these 2 weeks in doing the relationship matrix. So I'm also going to do an example of this in class. So I'm going to talk over the slides a little bit condensed, because they're also mostly self-explanatory and they're also in the textbooks for the class. But what's important is that you set up the customer needs. So the customer requirements, the what's for what your design needs to do, the technical response or the product requirements, so the how's, and those get more into, let's say the customer wants the boat to go 20 knots, and then the how is you have an engine with so much power, so that's measured in watts, and that's the engineering technical response. And then in this relationship matrix, you can indicate how well they're correlated to one another, and you can get some weighting through this entire house to start looking at the interaction between customer needs and technical response. So this is what the house looks like when it's filled out a bit more. Note, assume that the Kano analysis, we didn't do that this year, we just did the customer needs survey. So from your customer needs, or things from your team that you might have found from your research, you write a list of customer requirements, and then you have your engineering requirements across the top, and then you rank in this matrix a level 1, 3, or 9, weak, medium, or strong relationship for how much a customer requirement relates to the engineering requirement. So for instance here, a customer requirement is you need a large vehicle, and that's going to relate strongly to weight, but it does not relate strongly to carbon dioxide emission. So you can see the symbols they have in the matrix here to indicate that. And then at the top is what's called a correlation matrix, which is where you see how much the engineering requirements interact with one another. So for instance, weight interacts with dimension quite a bit, whereas drag coefficient and cost of production have a negative correlation. And so this is where it's important to use units in describing these engineering requirements, and also to indicate the direction of improvement to solve this logic at the top. So weight going down is good, dimensions going up is good because you can carry more. But depending on your design, dimensions going down might be better. And the rest of the matrix is things like to the right, you have your benchmarks, so you can see how well they do in solving the customer requirements so that you can get an idea of what a new design should be able to at least match or do better than. On the left, you weight the importance of the customer needs, and then by indicating how strong the relationships are throughout the matrix, you can solve for importance rating and percentage at the bottom to tell, for instance, cost is influenced by a lot of these engineering requirements, so it turns out being an important variable. And then the engineering requirements, you can see at the bottom, weight has a score of 471, so most design decisions with weight are going to affect customer requirements to a greater degree than something like CO2 emission that only has 100 down at the bottom. And so this slide just goes through a bit more details. You can see how to solve the equations on the slide based on the weighting. And this example is for an SUV car, but generally you would conduct a similar set of steps for any mechanical design. And a lot of things like weight and dimensions are going to be in almost any mechanical system, and same as cost of production, and things like low cost and aesthetic appeal are generally always in every type of design, and safety. And here is the last slide that goes through a little bit more of the description. And so we'll be doing the House of Quality, like I said, in class. We'll start part of it next week, and then we'll finish it the week after that. And this is something that you're going to need to do with your teams for your project, for your report. And then also it's something that you're going to need to do for your individual project report as well this semester.